So I could either just do a file open in here, or I can just drag this file from the Windows Explorer into Visual CAD/CAM's workspace. Okay, so we got the part loaded in here. Is this part supposed to be in millimeter units?
It should be, yep.
Okay, all right. And this looks like a table leg, is that right?
Yes.
Okay, now parts like these can be programmed using a combination of indexed and also continuous 4-axis toolpath methods. So the first thing we would need to do here is define the machine tool, and also then we have to establish the orientation for it. So let us go ahead and define the machine tool in here. So we'll go to the machining browser. So if you're unable to view the machining browser, you want to make sure you click on Visual CAM and then select Mill, and that would display your machining browser. And on the machining browser, you have two main tabs. You have the Program and then the Simulate tab. Now on the Program tab, you would want to select Machine Setup, and we would define the machine tool as a manual definition, and we would set the number of axes in here. Since you would like to program this on a rotary axis, there would be a 4-axis.
Yep.
And as you're going to be rotating the part on a rotary chuck, you would define it as a table configuration.
Okay.
And once you define the configuration as table, you would then also define your primary axis, which is your rotary axis. Is your table, a rotary table, rotating parallel to the X, or would it be rotating parallel to the Y? So you would specify...
Yep. It's parallel to the X on this case.
So we parallel to the X. So when you select parallel to X, you could be defining the rotary axis as positive X or negative X. So a typical scenario for a positive X, it would be the rotary chuck is over on the left side as you face the machine tool, and your rotation direction arrow, as you can see, is along the positive X. So which means as you point your thumb in the direction of the arrow and roll your wrist towards you, that would be a positive, like a clockwise rotation, and then the other way around is a counterclockwise rotation.
Okay.
So you would choose between positive or negative X. Now, on most machines, it would be a positive X, but on some machines, if the chuck is mounted over on the right side, you may have to flip that over to a negative X.
Okay.
Okay, and you can leave all the other parameters at the default settings, and then select OK. You'll now notice that the machine tool is defined as 4-axis.
Okay.
In the next step, we would like to select the post processor for the machine tool that you're going to be working with. So we have all of the available post processors, and almost all posts are configured for 3 and 4-axis output. Would you be able to tell us what is the machine or the controller that you're going to be working with?
Yes, we just installed the new version of Mac 4.
Okay, Okay, so I have Mach 3 in here, so I'm sure that the Mach 4 would be very similar to Mach 3, but we can use one of these existing post processors and also modify it to Mach 4. So we can use the post generator to make edits, make changes in here. You can see that the rotary axis is defined as primary as A axis right in here.
Yep.
Now, if your machine calls it a B or a W or whatever the rotary axis code is, you can update it in here and save this as a new post for Mach 4. And I've selected the post that will output in millimeter units, and output file extension will use .nc, or you can do .text or .tap, whatever is your preferred extension.
Okay.
Okay. Now we established the machine and the post processor. The next step, before we define the stock, we need to orient the part. So the part is being aligned along the rotational axis. Now there's a couple of different ways how you can orient the part. So the first step we need to do is rotate the part in here. So you can select the part, you can use the manipulator tool in here, the graphical manipulator, and I can specify the angle to rotate it, and I can specify to rotate it 90 degrees, and you'll notice that the part is now rotated. So that's one of the ways how you can rotate your part. Okay?
Okay, I usually use the orient part button, but I didn't see where is this manipulator.
So the manipulator is found on the
Uh-huh.
status bar down at the bottom.
Okay, I see it now.
Now once you have this toggled on and you select the part of the object, it'll display the triad, and also it gives you the controls for rotation. If you need to translate it, move it, you can use the translation commands, or you can even click on it to enter a value for translation. Put in, for example, -2 millimeters, it'll basically go back -2 millimeters. Or you can
Great.
use the rotation commands as well. Now we could use a combination of different transformation commands. You could also select the part, use the modified transform tab, and use the transformation tools in here, or you could use the setup and then the orient part command in here also to orient it. So whatever approach or method that you feel comfortable with, you could use that.
Okay.
Now typically on a 4-axis setup, you want to make sure that the center line of the part is oriented along the rotational axis. Now the easiest way to do that would be by using the align and then set world coordinates. We can choose to set it to the part. We could do mid-Z and then west to start with. So that'll basically orient it. As you notice, it'll put it right in the center line of the part, right?
Okay.
Now if you need to rotate the part, so if you take a look at it, the part, if you need to, the initial orientation as you take a look at it from the top view, right, that would be the initial orientation. Now do you need to further rotate the part? Do you want to make any changes or to the orientation? You could always do that.
Okay.
So if you need to rotate it on the Z-axis, you can select the part and use these controls if you need to rotate it, or you can even specify an angle in here to rotate it about, I could say 45 degrees, and I can rotate the part to the initial orientation. Okay? So now if you
Yep.
take a look at it from the 4 views, the part is oriented, and also I do see that some areas on the part are below the rotation center, like for example these areas. So if you draw a center line in here, some of the areas are below the rotation center. So on 4-axis toolpath methods, you will not be able to cut below the rotation center if you're doing like a 4-axis, for example, parallel finishing. So we may have to use a combination of indexed and a combination of continuous methods to program this part effectively. Okay?
Okay.
All right. Now, any questions so far?
Can we move the parts so there are no parts below the 0 line?
Yeah, so meaning this section in here, you want to move it up slightly. I could say move it up by 2 millimeters. That was too high. I can go down maybe -1 millimeter. So now we moved it, but then you have a little portion that's sticking below the rotation center in here, right? So I'm going to go down by -0.5. So you can specify the distance you want to move it around. So also if you take a look at it from the side view, you see that it's kind of bent over here in some areas. So it's really not on the rotation center, but we'll show you how we can still program it using a combination of continuous and index 4-axis operations. Okay?
Okay. Yep.
All right. Now let me create the stock in here. Would you be starting out with a rectangular stock or a round stock, a cylinder stock?
Rectangular.
Rectangular. So we'll create a box stock in here. We'll select copy model bounding box, and it displays the length, width, and the height. So it shows that 13, 14, so it looks like the part seems to be the units. If you look at the length, width, and the height, the actual, even though we are in millimeter units, these look to be smaller, so it may have been inch units. So does the model needs to be scaled, or what is the extent of the part that's supposed to be in?
It should be around 35 centimeters, so 350 millimeters. I think we should scale that.
Okay, so the part what we imported That's in centimeters. So if you look
Mm,
at the length, do we need to scale that by 10 times? Because centimeter to millimeter is a 10 time, right?
yeah, but I think the original length of the leg was 35 centimeters. So I think we should scale that in 20. I don't know. This was bought by some website, so I
Okay.
really don't know which units were used.
So we could do a transform and a uniform scale, and then we can specify the length. You can specify the length in here. So if that needs to be, you said 35.
Yeah.
So yeah, if it's 35, you're basically scaling it about 2.596.
Is that in millimeters?
Yes, it is in. It is now representing the length would be 35 millimeters.
Uh, I meant 350.
Okay, should be 350 millimeters. Okay, so it'll be 25.9. So basically, it looks like I need to scale it to inches. 25.4 gives you the conversion factor in here. So we'll just do a transform and a scale, and we'll scale it to 2 millimeter. We just need to scale it by 25.4, and that'll do it.
Okay,
So that'll bring it to 342 millimeters and 130 and 130. That
perfect.
should be correct. Okay, so now I rescale the part. If I go back and go to quad view, you can see that the part is scaled, and I'm going to go back and redefine the stock in here. And now you'll notice that the length shows as 342 millimeters, the width is 130, and also the height is 130 millimeters, a little over 130.
Okay.
Now I can extend the stock if the stock that you're going to be starting with is going to be larger than this in terms of length, width, and the height. You can always specify these dimensions in here. Now for the purpose
Okay.
of demo, would you like me to leave it the way it is, or would you want me to
Yeah,
change the stock dimensions?
it's okay.
All right, so we'll accept that, and then we'll go back and align set world coordinates. I'm going to pick set to stock, mid-Z, and west. You can
Okay.
establish the XY0, Z0 over here, mid-Z and west, or you could put it to the top. So depending on, where you would like to establish your XYZ0. So if you take a look at the stock, currently your XYZ0 is defined right over here. The center in the Z axis, and
Uh,
also center on the X and Y and the back face of the part.
We usually work like this. Yep.
Okay, is this a good place to set your XYZ0?
Yes.
Okay, perfect. Now the next step we want to do is make sure the rotation center is on the center of the stock blank. So you can go to machine, and you want to make sure that the rotary center in this case is 0, 0, 0.
Okay.
Okay? Alright, so we established the part, we established the stock, we established the origin. We are now ready to program some toolpaths. So first I'm going to just hit save to save off the work in here.
Okay.
So we'll save the part and then we'll continue programming it. Any questions so far? So now we're going to go ahead and program some toolpaths. The first step is you need to create some roughing operation where you're going to be, roughing it out in levels, where you'll be basically going from the initial stock that you have down to the actual part itself. So that would be done using an indexed operation. So we would start with a roughing process. I'm going to use 3 axis. We'll select horizontal roughing.
Okay.
And then I'm going to specify a tool in here. And we could start with a 1/2 inch or 3/4, whatever size end mill that you'd like to go with. Do you have a preference on what size tool would you like to use?
No. Any of
Okay,
those is
so I'll use a 1/2 inch. We'll go to set the feeds and speeds. We can specify the clearance. So very similar to how you program 3-axis operations in here. You specify your cutting conditions where you can set the tolerances in here for roughing. I'm going to go with 0.05 tolerance. Stock to leave, I could say leave 1/2 millimeter of stock above the part in the
okay.
roughing process. Choose your cut direction in here. Specify your step over. In the cut levels, we would want to specify a step down and probably just go halfway down. So I can specify the step down to be like a mid-plane, right? or I can go slightly below the midplane. I could say -2 millimeters, maybe slightly cut below the midplane. Okay? Or
Okay.
you can specify the value in here. You can even use the pick option in here to pick a point, and you can say you want to snap to a point near, and I can just go pick that point, and that'll determine that value is slightly over 3 millimeters midplane. Okay?
Okay.
And then you can specify your engage and retracts, any advanced cut parameters, like if you want to perform arc fitting. So typically I do the arc fitting to be the 2 times of this tolerance in here, so which is 2 times perform arc fitting. Okay?
Okay.
And then select generate. So in this process, a 3-axis roughing operation is generated based off the part and the stock geometry. So we now have a roughing operation programmed, and it's roughing it from the initial orientation where your rotary table is at 0 degrees. And you can always control the parameters, your step overs, step downs, and in how many number of passes you would like to rough it. So I'm going to do a pause and then pick simulate to end, and this shows the roughing process from the top side. Okay?
Okay.
Now we would like to rough it from additional sides. I would use an indexed operations. I would go under setup. So I need to rotate the rotary axis or the rotary table, and in this step I'm going to rotate it by 180 degrees. And they'll pick OK to accept it. So now the Z-axis, as you can tell, is inverted, which means the rotary axis would be rotated by 180. So you're seeing the display of the world coordinates. The ones with the labels X, Y, and Z are the world coordinates, and the ones without the X, Y, Z labels are the machine coordinates. You can actually toggle off the world coordinate system display by selecting hide or show WCS. So that way what you're looking at is the machine coordinate system display. You have the setup 1 is your rotary table is at 0 degrees, and then the setup 2, which you just rotated it by 180 degrees.
Okay.
So the rotary table would be rotated by 180 degrees. And now I'm going to program the roughing operation in here, right click on it, select copy, and then I can paste it below setup number 2, and I can make any changes in here that are needed for the cutting parameters. I can adjust the Z value in here, I can lower it, or I can specify how far I'd like to go, or just stop it at the Z0 plane, and then I pick generate. So in this process, it's going to compute the roughing toolpath after the part has been rotated by 180 degrees. So you don't have to rotate the part in Visual CAD/CAM. We are just rotating the view, but we rotated the coordinate system by using this rotate table setup.
Okay.
So now you're noticing that the roughing is performed from the 2 sides.
So in setup number 2, when we extract the G code, when we post it, we will have a command which is saying to the rotary axis to go A180. Yes?
Yes. You could post the entire machining job. Right click and select post all. And when you post the entire machining job, in your posted code, you'll see that the A is output as 0 for the first setup. And then we would do a search for the next rotation. You will notice that the A goes from 0 to 180 degrees under the second setup. So the A goes from 0 to 180 for the setup number 2 when it rotates it. Okay?
Okay.
So the A would go from 0 to 180, and your rotary axis parameters are all set up in your post processor in here. So you define your rotary axis macros under the multi-axis motion, under the setup tab, and it rotates from 0 to 180 degrees.
Okay.
Okay. Now once you have programmed the 2 setups in here, so you have your 0 and you have a 180, right? So if you just post one of the setups, it'll output a 180 as well. And then you want to rotate it back to 0 to start the finishing process. Now if you want to program any additional operations in here, you can add some additional roughing operations as well. But in this step, I'm going to rotate it back to 0 degrees. So I'm going to rotate it back to 0, and I'm going to program a 4-axis finishing toolpath. So I'm going to use 4-axis, and in this particular step I'm going to use a parallel finishing. We'll specify a tool for it, so I would like to use typically a ball mill for finishing process. I'm going to use a ball mill.
Okay.
And then specify feeds and speeds, specify clearance. Now when you do a 4-axis continuous operation, you'll notice that your clearance is represented as a cylinder clearance rather than just being a plain clearance as in 3-axis operations.
Yep.
And now you specify your cutting parameters. You can set the low value and the high value, which represents the extents how far you're cutting. So you can specify these values in here. You could say you want to leave maybe 1 millimeter off the sides. You can put in the value right there. So it'll stay 1 millimeter off the edge if you don't want it to go all the way to the back of it. And the same thing can be done over here. You can keep it short by specifying you only want to go to 340 millimeters. You can set the low and the high values.
Okay, so the tool doesn't go out.
Right. And you can also set whether you want to go 0 to 360, so that would be the entire rotation. You can choose your cut pattern. You could go along or across axes. Cut pattern could be zigzag or zig. You could choose all of these parameters, control or set the step over. You can also control the step down in here. So if you have features that are dipping below the rotation center, I could say do not go below like a 1 millimeter or half a millimeter below the rotation center. So you can see that there's a small portion of this stock that's dipping below the rotation center. So if you draw like a center line, you will notice that there's a small portion that dips below the rotation center, right?
Okay.
So you can adjust the part and the stock part slightly to be above the rotation center, but if there are features, then you want to avoid that. So I can put in 1 millimeter. So anything that's below the rotation center, it's a radius of 1 millimeter. It's not going to, cut those areas. And now I'm going to select generate, and in this particular step, it's going to create a 4-axis finishing toolpath. So now you have a 4-axis continuous finishing toolpath. The tool path, what you see that's generated in here is basically going along the axis, and the tool remains normal to your rotational axis. So when you run a simulation, you'll notice that actually the part rotates, but in the simulation you're noticing that the tool is going around the part.
Okay.
So what you're performing here is just a cut material simulation. If you perform a machine tool simulation, you will notice that it's the part that actually rotates.
Okay.
So this would be a continuous 4-axis finishing operation. So you'll notice that on this particular part, for most areas, most part of it, we were able to program it using a continuous operation. Right?
Perfect.
There's a small section in here, since the section was dipping below the rotation center, we weren't able to cut that area with a continuous 4-axis toolpath. Now you could do a combination of indexed operations. You could do rotate table setups, maybe rotate it like a 45 degree, or you could pick one of the orientations and program it, or you could even just do a 3-axis looking down from the top orientation. You could just do a parallel finishing in here by defining a boundary or a horizontal finishing. You can create a boundary, curve boundary in here. I could just use a simple polyline, or I could even draw in a rectangle. So I'm just going to create a polyline in here, use the polyline command, and I could say this is the area I would like to go back and refinish. So I'm going to basically just create a little geometry right there, and then add a 3-axis parallel finishing operation. I can pick this as the cutting boundary, the containment boundary, specify the tool, and then set the cutting parameters. I could set the angle of cut and then generate. So in this particular step, it's going to go back and create a finishing path just to program that particular area.
Okay.
So you can define specific areas, and then still do a combination of both index and continuous operations. Now when you post-process the parallel finishing, I'm going to do that right now. And you'll notice that in your posted code, you have your A values, which represents your rotation axis code. You can see that the A goes from 0 and increments all the way to 360.
Okay.
So you have your x-axis, z-axis, and then the a-axis motions.
Perfect.
Any questions so far on programming this part?
No.
Okay.
It's all very clear.
Okay. So this would be a typical workflow. There are several other types of 4-axis methods. We have 4-axis facing pocketing and profiling. We have 4-axis R-level finishing, parallel finishing, projection pocketing, engraving. Also, there's a new method called drive surface machining in 4-axis. So the drive surface machining uses the surface normals of the surface for programming. So in this case, you happen to have like an STL file. So the STL file can be used as a surface to check for, so to project to, but you can't use that as your drive surface, so you need to actually draw or create a drive surface, and then the tool can remain normal to that drive surface. So I can give you an example for some of the other toolpath methods in 4-axis. Now before I do that, I wanted to find out if there's anything in addition to these you wanted me to help you program it on this particular part.
No, I think I understand everything, and tomorrow I will do some testing. So if I have any more questions, maybe we can do a different session.
Okay,
but
sounds
so
good.
far everything has been very well explained.
Okay, great. So I have an example for 4-axis drive surface machining in here. So if you analyze this part in here, there are certain areas of the part that are below the rotation center.
Yep.
So the surface itself is just a linear extrusion. So you can draw a planar curve that is normal to the axis of rotation. So since the rotation axis is on the x, the planar curve is created on the YZ plane. And then if you extrude this curve, that creates the surface, right?
Yeah.
Now, you can use this method called 4-axis drive surface machining, and you can actually pick these surfaces as your drive surface for machining. And you want to make sure that your surface normals are pointing in the correct direction. So you want to make sure the surface normals are pointing away from the surface. Okay?
Okay.
And you specify a tool. So we'll use a end mill or a ball mill. Specify your feeds and speeds, your clearance, and now you can choose whether you want to go along or across axis. In this particular example, I'm going to use across axis since the previous part that we demoed, we used along axis, and then I'm going to select generate. So this method will be able to help you program undercut areas. This is a drive surface machining method, so you can program very efficiently program undercuts. Now if you had an additional surface that's wrapped on top of this, the toolpath will actually be projected onto that surface.
Okay.
So now I've defined a stock using stock from selection in here. So I have a stock that's actually an offset of the actual part itself. If you run the verification, you will notice that the tool is actually being normal to the surface at all times. So the tool is normal to the surface. So if you just did a 4-axis parallel finishing, your tool remains normal to the rotational axis. That's why you can't cut below the rotation center. But with the drive surface machining, the tool remains normal to the surface. However, you need to make sure that the drive surface, what you're defining, is normal to the axis of rotation. So basically like an extrusion, right?
Okay.
So this is how you could program a drive surface machining toolpath.
That's interesting.
Now these methods are available in expert and pro configuration, the 4-axis methods. Now I would recommend the Pro configuration as you can take advantage of all of the 3-axis advanced methods as part of indexed 4-axis, which means when you do rotate table setups and program an indexed operation, you could use all of the advanced 3-axis methods like re-roughing. So if you do the 90-degree rotation as opposed to 0 and 180, rather than doing a roughing, you could do a re-roughing so it knows what is the stock being left from the previous operation to program a re-roughing operation. So that would be very beneficial, in a lot of your applications when you're roughing it out from a large piece of stock.
Yeah.
So this is called true 4-axis, or also known as drive surface machining. Now we have a 4-axis method to do instance repeat work or repeat instancing. So what I have here is the feature repeat itself on 6 of the sides. Consider you have like a hexagonal nut that's mounted on a cylinder, right? So we
Yep.
now have 3 operations programmed. These could be indexed like a 2-axis, 3-axis, or it could be even a continuous 4-axis operation. So we have these 3 operations: facing, a profiling, and a drilling operation program, and we would like those operations to be instanced or repeated on each of those additional sides. So rather than having to create a rotate table setup and program each of these as separate operations, one of the new features we've introduced in 2017 is the ability to perform rotary instance operations. You can select rotary instance and you specify the incremental rotation. So since there are a total of 6, if you do the math, 360 over 6 will be 60 degrees. I'm going to put in 60 degrees. I'm going to specify the number of additional rotations to be as 5, since we already have 1 plus 5 results in 6. So I'm going to hit generate.
Okay.
And now if I place the facing operation under the instance, you will now notice that it creates those repeats for each of them.
Mm-hmm.
So if you were on a verification, so you're just programming 1 and you're instancing it.
That's very nice.
So it automatically computes the...
And
Could you repeat that again, please?
I'm sorry, I just wanted to ask if this expert version.
Yes, the rotary instance is available in the expert version as well. Now,
Okay.
all of the 4-axis methods that you see under the 4-axis methods in here are offered in Expert, Pro, and Premium. Now, the indexed method is also offered in Expert, Pro, and Premium, which is a rotate table setup. Now, if you're going to be using 2- and 3-axis method with the indexed, the advanced 3-axis methods are only offered in Pro and Premium. So if you would like to use re-roughing on a rotate table setup, you would need to have the Pro configuration. Okay. Now you could also program 4-axis facing, pocketing, 4-axis profiling operation. Now these could be used for parts that have a constant radius. So if you have parts that are on a constant radius, like for example, consider a band where you want to program 4-axis facing, pocketing, or profiling. So I'm going to pull in an example in here that would give you a good representation of 4-axis facing, pocketing, profiling operation. So, or you can also perform drilling operation in here. So you can notice that the curves are actually wrapped onto the face of the cylinder. So similar to how we can do 2-axis, facing, pocketing, and profiling, you could do the same with the 4-axis operations as well. So there is a 4-axis method. If you go to 4-axis menu, you'll find facing, pocketing, and profiling. And these methods can be used for parts that have a constant radius. Now consider it like a wrapping and an unwrapping in 4-axis. And you can specify all of the parameters, like you can put in your depth in here. You can specify and it'll automatically figure out the angles to orient to those positions. So the angles are automatically computed. Okay?
Yep.
There's 4-axis methods like 4-axis projection pocketing. We also have 4-axis methods where you can perform 4-axis finishing in levels. I'm also going to give you a quick example for that, and then we'll go ahead and answer any questions that you may have, and we'll go ahead and wrap up the demonstration for today.
Okay.
Would there be any questions so far?
No.
Okay, so I'm going to go ahead and bring in an example for 4-axis projection pocketing. All right, so now what I have here is basically a part which has these cavities in here, right?
Yep.
So these cavities, you could program, you can start using a 4-axis parallel finishing operation, and then to program inside these cavities, you can use a method called 4-axis projection pocketing. So you would basically specify these as curve boundaries in here, and then program a 4-axis projection pocketing, similar to how you have the 3-axis projection pocketing as part of the advanced 3-axis module. Now the 4-axis projection pocketing is available in expert and professional configuration, so it can be used along a rotary axis.
Okay.
Now I could be programming a parallel finishing first to clear out the material in here before I do the projection pocketing. So it basically does a constant 2D XY offset, and then it's projected down to the underlying geometry.
Okay.
Now you could also be using 4-axis projection pocketing for shallow cavities. That would be an ideal example for 4-axis projection pocketing. And we also have 4-axis finishing in levels. I'm going to go ahead and bring a file to demonstrate that as well. Okay, so the same part what we looked at, we can also use a finishing in levels method. Now this could be used for steep areas. That could be like, you may have like prongs and features on a part that could be, sticking out, or you could have like cavities in here where you can do a finishing in levels toolpath. Very similar to your 3-axis horizontal finishing, so it does finishing in levels.
Okay.
So this method is known as 4-axis finishing in levels. So all of these methods, facing, pocketing, profiling, can be used for parts which has a constant radius. You could do R-level finishing, which is called finishing in levels. Parallel finishing, we looked at in the demo part that you had supplied us. We have pocketing, projection pocketing. We have 4-axis engraving, so you can have curves and text you can engrave, and also the drive surface machining. So these are called the continuous 4-axis methods. And if you would like to program indexed, you would use a combination of rotate table setup and then use combination of 2- and 3-axis operations.